Hi everyone, my name is Simon, Simon Brand. Some may know me better as Tartan Llama, where you can find me on Twitter and any number of social media places. So I'm a senior software engineer at CodePlay in Edinburgh, where we work on toolchains for heterogeneous systems, like compilers, debuggers, profilers for OpenCL, GPUs, that kind of thing. So I'm going to be talking today about how C++ debuggers work. Debuggers are kind of seen a lot of the time as a black box. We use them all the time, day to day, but so many of us just say, okay, we set a breakpoint and debugger does some magic. I don't care how this magic is implemented, but I'm going to show you how it's done. These are the points which I want to talk about today. So we're going right down to how are breakpoints implemented? How does the debugger implement single stepping, reading registers, that kind of thing? Towards the end, I'm getting into some more advanced topics, so I'll be kind of just breezing over them. But hopefully you'll kind of get a taste of all these different areas of debugging. Because we've got a lot to cover, if you need anything clarified during the talk, then please just raise your hand and ask. But any longer questions, please leave until the end. Also, if you see this, find the bug, then we're going to be doing some live debugging of C++ code. And you guys are going to be finding our bugs. A little bit about my background in debugging. So as I said, I worked for CodePlay. I've worked on a number of production debuggers for HSA and OpenCL. They're largely based on LLVM's debugger, which is called LLDB. And I've worked a lot with formal standardization for the HSA tools and with the dwarf standard, which I'll talk a lot about today. First question, of course, is what is a debugger? Does anyone know what this is? Yes, at the back. Yes, Gracehopper found this moth. You can kind of read it there in the terrible resolution. First actual case of bug being found in a relay. So most of our debugging doesn't really look like this. We aren't going into machines with our hands and finding moths. We're more likely to look like this, which is the command line interface for LLDB. Maybe yours looks like this, which is GDB running side Emacs, or whatever text editor you prefer. Maybe it looks like this, the curses interface for LLDB. Or maybe you like GUIs and you use Visual Studio. So these are all kind of different flavors of debuggers. What ties them all together is they're applications which are used to test and debug other applications. It's kind of a nebulous description which could apply to a lot of things. So a little bit more concretely, these are the kind of main operations which you want to do in a debugger. You want to be able to set breakpoints on your high-level source code, maybe at the assembly level. You want to be able to step through your code. You want to be able to evaluate expressions in your source language. And you want to be able to view the backtrace. So if you like segfault, you want to know where you came from. How did I get there? So I'm going to be talking about all of these points and more. Before we get started on all of this actual stuff, I'm going to talk a bit about the platform I'm going to be using. So as you might imagine, debuggers are very platform specific. Not only the architecture they're running on, but also the operating system, any number of other things. So for demonstration purposes, I'm going to be using x86 Linux systems. So a bit about that. Linux is, I'm sure you all know of it, so this is the main operating system we're running on. x86-64 is the architecture I'm going to be talking about. Does anyone know what ELF is? Raise of hands just so I get flavor. Quite a few people. How about dwarf? About the same. So ELF and dwarf, respectively, are the main object file formats and debug information formats. And those are the ones I'm going to be talking about today. Then PTrace is Linux's kind of OS level debugging interface. This is a fairly good overview of ELF in a nice pictorial form. What it essentially is a architecture-independent way of expressing some kind of binary. So it's split up into some header information, which tells you about the architecture it's going to be running on, a bunch of stuff about the program itself. And then there'll be a lot of sections, which might hold your code or your static data, and those are all in a well-defined manner. So if you follow the ELF specification, then you'll be able to parse and understand these binary formats. Debug information, as I said, we're using Dwarf. For the most part, debug information in Dwarf is expressed in Dwarf information entries, also known as dies. So this is an example of a die for a compilation unit, so like a file, kind of. So you can see it has a tag, which tells you what kind of entity is being represented, and then it has a bunch of attributes. So this tells us what compiler produced it, in this case Clang, the language which was produced for, because Dwarf can be used for any language, it's not just C or C++, the name of the file, which the compilation unit was derived from, and then more information such as the program counter ranges for the program. It will also tell you line number information, so you need to be able to, in your debugger, map from your high-level source code down to the instructions which are running on your machine. And so the line table allows you to do that. So this is essentially a mapping from addresses to high-level source lines. This is kind of the format which Dwarf dumps, the utility prints out. The actual format is very, very compact and expressed as kind of a program which runs inside the debugger itself. PTrace is very, very powerful, but also kind of ugly. So it has 4 arguments. It's just a single syscall. And the first is an enumerator, which tells PTrace what to do. And this isn't just like a different flavor of an action. This is do something completely different for different actions you might want to take out. So you give it some request and some process ID, and then you give it maybe an address and some data. And these things mean completely different things depending on what request you make. So you might say, I want to allow tracing. I want my parent process to be able to trace me and read my registers and my data and things like that. You might want to read and write memory or read and write registers. So these are the kinds of things you can do with PTrace. Note that there's not an operation to create a breakpoint or anything like that. Those are higher level concepts which can be implemented using these lower level constructs like reading and writing memory. So that's a brief overview of the platform. So before we get started on breakpoints, we're going to find the bug. So raise your hand if you see it. So we got an unordered set. If we want it to be 2 strings, hello, and stop them. And then we want to iterate over this and output the string followed by world. However, this does not print hello world and stop the world. It does compile. Can anyone? Yes, there's a hand there. Exactly. So the correct answer was, this isn't creating a set of 2 strings, it's creating a set of a single string, and it's imagining that those 2 string literals you pass in are 2 pointers which create a range. And of course, that's garbage, because we've just got 2 strings and we're thinking that they're a range and they're not. So this is C++, it's great. Breakpoints. So I'm first going to talk about software breakpoints, and then I'll briefly talk about hardware breakpoints as well. So imagine we have some binary code. This is x86-64 assembly. And we want to set a breakpoint here at this line with the arrow. So what we do is we actually change the binary in our memory that we're executing. So what we do is you can see these bytes, which make up the instruction stream, which the processor is kind of interpreting as all of the instructions. So we take this first byte of the move instruction, and we remember it. We're going to need it later. Then we write in this value here, oxcc. Now this is a special instruction on x86 called int3, and this will trigger a software interrupt. So what happens is we've just modified the code which we're executing while the code is, well, the code has been stopped, but essentially while we're running the program, we've just manipulated the program itself. So imagine our program counter is on this first line here. Then it will execute it. It will move on to the next instruction. We'll execute it, and it will stop. We just triggered a software interrupt. So it's now up to the operating system, who has registered all of its interrupt handlers when the operating system started up, and it will have its own interrupt handler for this int3 instruction. So on Linux, this looks kind of like this. This is actual code from the Linux kernel. So you can see it's doing some setup, and then it's doing this trap. So what this does is signals the process with a sig trap, and this is going to be handled by the debugger. So again, just to walk through, we're here. We execute the instruction, we execute again, we stop, we drop down into our interrupt handler. So to show a kind of full example of this, say we have this situation. We have our debugger on the left there, and our debuggy on the right, the process we're debugging. They're both stopped. The debuggy is waiting for us to tell it what to do, and the debuggy has been interrupted or hit a breakpoint, whatever. So if we ignore the debuggy for now, we input some command, continue, press a button on Visual Studio, which makes the debugger run. It's now going to tell the debuggy to continue, and it's going to wait on a signal. So you can see here it's running. We continue the debuggy, and we wait for a signal. So the debugger is now stopped, and the debuggy is now running. So again, we've had our breakpoint set there that you can see with the CC. So we're going to execute the first instruction. We're going to execute the next instruction, and we're going to stop. Control flow is then passed to the interrupt handler, and the interrupt handler is going to send a sig trap, which is going to be taken by our debugger, and it's going to continue, and it knows we've got a signal. This is how software breakpoints work on most CPU architectures. The instruction for breaking will be very different, of course. You can't just write oxcc in ARM and expect it to work, but it follows the same kind of procedure. So again, we're just manipulating the code, breaking down into the operating system, getting a signal. So now our debugger can say, okay, well, I stopped, I got a signal. It can look, it can see, okay, it's a sig trap. I know that means I've hit a breakpoint or something. It can then get some more information from the operating system and say, okay, why did I get this signal? Was it from a single step? Was it from breakpoint? Was it from like a thread being spun off? And it can update its own internal data structures. It can say, okay, where is the program stopped? And it can then move on from there. Does anyone have any questions about how software breakpoints work? No, cool. So say we want to break at main, very simple kind of hello world of debuggers, if you will. Then what we do is we can't just kind of say that to the processor, I want you to break on main, because it doesn't understand what main is. It has instructions and addresses and binary, but it doesn't know what you mean when you say main. So what you need to do is consult the dwarf information. So you can look for a subprogram, which is like a function, and you can say, okay, this one's called main, that's what I'm looking for. You can look at the low PC value here, and that tells you where the function is going to be loaded in memory. So this will be done depending on if it's a shared library or what have you. It might be done by the linker at link time, or when the shared object's loaded into memory to be executed. So we can then just set a breakpoint on that low PC using the same kind of thing which we just saw, and it will work in exactly the same way. If we want to set a breakpoint on a source line, which is kind of the other main kind of breakpoint you would want to set, then we can set up the line table information. So we want to set a breakpoint on line 4 of foo.cpp. So we have a look here. We can see foo.cpp is there. And we can see line 4, which is here. Now this corresponds to the address OX400686. So we can just set a software breakpoint there, and it'll all work. So this is kind of how the low-level interface is setting breakpoints on addresses, and then we map this to the high level using the dwarf information. Hardware breakpoints are very, very hardware specific, as you might imagine. But generally, you can set kind of some special purpose register with an address, and the processor will make sure that you get a signal when that address is either read or written or executed, depending on some flags you set. So now this is quite powerful because with software breakpoints, we can only tell it to break when the line is executed. But with this, we can say, if something reads this address, I want you to break. I want to be notified about it. So you can use this to set watch points and things like that. So it's very powerful. However, because it's using dedicated hardware, it's quite limited. So on x86-64, for example, you only have 4 of these registers that you can set at any one time. So in a normal debugging session, if you're setting like, I don't know, 20 breakpoints, maybe you have overload sets, maybe you set 200 breakpoints. You can't do that because you've got 4. So that's breakpoints. Before we move on to stepping, another bug to find. So here we have a map from 0 to 1, 2 to 3, 4 to 5. We're iterating over the pairs which it stores, and finding the one which where the key is 2, and then storing a pointer to its second value. Can anyone tell me why this does not output 3? Yes?
Must be constant as the key.
Yes. So the map iterator does not dereference to a pair of int. It dereferences to a pair of const int, because you can't change the key in a map. So what this does is it creates a temporary, and it binds that const reference to the temporary. So then when you assign the pointer, it's a dangling pointer. Great. Implicit conversions, yay. Stepping. So there are 2 kind of main types of stepping which you'll want to do in your application. One is at the assembly level, and the other is at the high-level source. So at the assembly level, you want to step by instruction, and at the high-level source, you want to be stepping over entire statements in your code or expressions. So the instruction step on x64 is actually very, very simple. We just tell PTrace, we want a single step. And it will handle everything for you. You'll get a signal when the step is finished, and then you can go on your merry way and do whatever you want. To step out, you can pretty much set a breakpoint on the return address, and you can know that by looking at your stack or a bunch of other ways. To step in is a little bit more complicated. So you want to step into function calls. If you're going to call a function, you want to be in that function. You don't want to move over it. So you can set a breakpoint at the return address just in case you jump back. And then you just need to set a breakpoint at kind of the next statement. But the problem is it's not usually clear what the next statement is going to be, because you might branch, you might have a go-to if you're suitably annoying, you might have any number of things which could happen. So you can't just kind of say, oh, next statement, set a breakpoint, yeah, it's done. You have to kind of look at what are the possible branch targets of the instruction. Where could I go from here? Am I going to jump over here? Am I going to jump over there? Where do I have to set the breakpoints? So that can take the form of some kind of emulation of the instructions. And that's the kind of thing which you need to do if you don't support a hardware single step like this. You have to do exactly the same thing. So a lot of processors, like I think ARM processors, don't have a single step, so you have to do kind of instruction emulation or something like that. Step over is very similar. You want to step over the function calls, so you can set a breakpoint at return address and at the next instruction in this function. So that's kind of a very simplified view of it. Real debuggers have this idea called like a thread plan, where you can kind of build up a bunch of operations which you want to do with your threads, and then those can be handled by the debugger. So if you hit a breakpoint while you're stepping, then you don't just lose all your state. So there are so many edge cases in debuggers, and single stepping when you have breakpoints and multiple threads is a nightmare. So this is very simplified. So moving on to registers and memory. Getting registers using PTrace is actually a lot easier than you might think. You can just give it this user reg struct. You say, PTrace, get me my regs. And PTrace gives you your regs. So it gives you a structure kind of like this. And it just has all your registers as values in there. So you just get the structure, and you can, if you want to get the program counter, then you just read regs.rip, and it works. So it's, although I hate PTrace in so many ways, this actually kind of works. Then if you want to write your registers, you can just write, I'm changing my program counter to 0x42, and then you say set regs, and it will set all the registers for you. You don't have to do anything else. So this kind of stuff is done a lot in the debugger, especially manipulating the program counter, because you need to reset the program counter every time you hit a breakpoint because it's stepped over the breakpoint, things like that. So the debugger is doing a lot of this behind the scenes, even when you're not recognizing it. If you want to read and write memory, you can use PTrace. You could peek data and poke data, give it an address, maybe a value. But the problem with this is it's reading and writing a word at a time. So if I want to write 1,000 words into my memory, I don't really want to make 1,000 syscalls, like, if I care about perf at all. So Linux provides us this process VM readv and writev, which you can kind of give it descriptors for the size of the data you want to read and write, how many, all of this kind of stuff. So if you want to do reading and writing memory in blocks, then you want to be using this, not PTrace. For words like setting a breakpoint, PTrace is okay. Stack unwinding. Again, stack unwinding can get very, very complicated. So I'm going to present the kind of simplest case of it. So this is what a stack on x86 64 could look like. You've got your arguments to your function at the top there. You have the return address for the function when you want to get back to where you were. And then you have the frame base pointer for the previous function you were in. And then after that, you can have all your local variables, and it will get bigger, whatever. So say I have this short excerpt. I have foo, bar, and baz, and they call each other up. So if I hit a breakpoint in foo here, I want to know how I got there. I want to say like backtrace, and it will give me foo, bar, baz. So how does the debugger actually know where we got to? So if you're the debugger and you hit a breakpoint in foo, you kind of have this information. You have your stack, you have a return address, the frame pointer to the previous frame, hopefully, if your compiler hasn't elided it. So what you can do is you can walk back through the stack like a linked list through all of the frame pointers. But again, this just gives you another stack. I don't know where this came from. I don't know what function this is. But I do have the return address, so I can look at the debug information. And this tells me, oh, I'm in bar, because I'm between this range of program counters. And then I can walk back, and I can say, oh, I've got another frame. What's this? Oh, well, I look at the return address. It's baz. And I can do this all the way back until the ABI tells me to stop. In this case, when this saved RBP is 0, I stop, and I know I've hit the top. And then I can tell the user, here are all of your stack frames, and you can give it as much information as you have. So that's it for stack unwinding. Expression evaluation. So say I have a program, and I have an int, and I want to print it out. This is a fairly simple use case. And what I can do is, I can just look at the debug information. So I have a variable called myInt. You can see the name matches there. And this tells me its location. So this tells me that it's at an offset of -8 from the frame base. So I can just look there. But the problem is, I need to find the frame base. And that's not so easy in a lot of cases. Sometimes the compiler will just track it in a single register, so you can just read that and it's fine. But compilers like to optimize things, understandably, and they don't want to use an entire register when they don't have to. So a lot of the time they'll omit this pointer and they'll tell you, oh, go and look at the exception handling information, which is stored in your ELF file. So that's the second case there. It tells you to go look at the exception handling information and use that to unwind the stack or find where your frame base is. And then it could possibly give you a location list like this, which is essentially if you're between these program counter ranges, then your variable's over there. And if you're between these program counter ranges, it's over there. So there are a few different ways which it can be expressed, and the debuggers have to deal with all of this. So it quickly becomes complicated when you have to deal with all the use cases. If you've got an expression like this, it's a little bit more complicated. I can't just go and read memory and it will tell me the right answer. I need to understand what it means to multiply my int with a. So what you can do and what LLDB does is you can wrap it up in a function like this. So this is just a C function, essentially. Well, C++ function with some kind of LLDB-specific things in there. And it can just generate LLVMIR for that expression, and then it can interpret it and give you the right answer. So you're actually kind of calling out to your compiler saying, I have this expression, I don't really want to implement a full compiler in my debugger, so I just use Clang. And it will generate me IR, and I can then interpret it and get the right answer. If it's something like this, it can be a little bit more complicated. Say foo has side effects, does some I/O, or volatile accesses, whatever. Then you can't just interpret IR for that. It doesn't make sense because presumably you want these side effects to happen. Otherwise, you wouldn't be calling the function. So what you need to do is pretty much the same thing, wrap it up in a expression, generate IR for it. But then instead of interpreting the IR, you JIT it onto your system into the memory space of the process you're debugging, and then you execute it. So it's just as if it'd been called within the program. You're just kind of generating the code at runtime and jumping there, and then jumping back. So that's how most kind of expression evaluation engines work at a simple level. So last find the bug for this talk. We have a variant of a std string and a bool. We set it to hello, then we get the string, add world, and print it out. It compiles, doesn't do the right thing. Can anyone tell me why? Yes, Matthew? Pardon? Yes, exactly. So this does not create the std string in the variant. This creates the bool, because C++. So the conversion from the string literal to std string will use a user-defined conversion, but the string literal to bool will just be a built-in conversion. Checks if the pointer is not null, which it won't be because it's a string literal. So this just stores true. So you get a bad variant access or whatever when you try and do this. Multi-threaded applications. As I said, we're getting now to the point where these topics are far too huge. I'm going to gloss over them very quickly. So PTrace lets you, depending on what your kernel version is, you can set an option to say, when I clone something, I want to get signal back. So when you create a new thread in Linux, the clone syscall is used. And this will give you back a sig trap whenever this occurs. And then there'll be some information attached to that signal which says where it came from. So I can say, oh, was this from a clone? oh, it was. So I can update my own data structures, I can get more information, I can get thread ID, I can update all of my kind of understanding of this application, and then I can keep going. Because in Linux, threads are pretty much just processes, I now am kind of tracking different processes at the same time. I've got multiple process IDs which I'm using, so it becomes very complicated very quickly. And that's even if you're just debugging on a CPU. When you get into the world of GPU debugging, and you have, yeah, I've got like thousands of PIDs. Great, what do I do with these? It becomes very complicated. Shared libraries. This is a really fascinating example of the interaction between your operating system and your tools. So if you're a debugger, you want to know when some shared library is being loaded. Maybe it's done when your program is started up and you've dynamically linked in something, and you want to be able to set breakpoints on like boost or whatever. Or maybe you DL open something or like load library on Windows. You want to be able to set breakpoints in these. You want to be able to step through and do everything you would in your normal application. So that means that the debugger has to know as soon as some library is being loaded, so that before you actually get there in your program execution, you can set all the breakpoints you need to. So the way which this is done in Linux is in your process address space, you will have a bunch of these entries stacked together. So this is just some tag and then either a value or a pointer. There are quite a lot of these, and they all mean very, very different things. But one of these will point to a rendezvous structure, rdebug. This has some information like the version and tells you a little bit about the state of this structure. And then it gives you a linked list of all of the descriptors for the libraries which have been loaded. So the really cool thing is this magic here. What this rbreak member is a pointer to a function. And every time some dynamic object is loaded or unloaded, that function's called. So what the debugger can do is it can set a breakpoint on that function. So it doesn't tell the user, just under the covers, it'll set a breakpoint there. And when it's hit, it knows, oh, something's changed. I can then read this linked list, and I can update my own internal data structures, set my breakpoints, maybe tell the user if they've asked for it, and do essentially everything you would want to do with shared libraries. So you can imagine the debugger's doing something kind of like this. Say the breakpoint function is called notify library list updated, and then you have some function to walk the linked list and print everything out. Then you can imagine you do something like you set a breakpoint, you run, and when you hit that breakpoint, you can, when your program starts, you can print the library list and you'll have anything which is loaded at the start of your application. And then you can continue, and then when something is changed, you'll get a breakpoint, and you can print the new library list and it'll have changed. So this is the kind of thing that the debugger is doing under the covers without telling you. So the main last thing I want to talk about is remote debugging. This is the kind of main situation you're looking at when you're doing remote debugging. You have some host system, your main laptop, desktop, whatever, and you have some target. On your host system, you have your debugger, which is running. On your target, you have the application you want to debug, and you also have some kind of debug stub. So this stub is supposed to be a very, very thin wrapper over your operating system's capabilities, like PTrace. In reality, this thing gets big. Like LDB's debug stub on debug builds is like a few hundred meg or something. It's ridiculous. It turns out that a lot of things have to be built into these debug stubs if you want to do things like branch target selection and things like that. It gets ugly. So what happens is the debugger communicates with the debug stub over some remote protocol, and then the debug stub communicates with the debuggy using your OS specific library, like PTrace. But actually, you probably do a lot more remote debugging than you think, because most debuggers do it even when you're just debugging on the same system. So if you use GDB or LDB, they don't kind of have a switch that says, oh, if I'm doing local debugging, I'm just going to call PTrace. And if I'm doing remote debugging, I'm going to use the remote protocol and then let the debug stub handle everything. No matter whether you're running on a remote system or your own, it'll spin up this debug stub and do everything in one way. It means that they only have to implement this remote protocol, and then they can kind of swap out the debug stub no matter what kind of platform you're running on. It also means you have a kind of separation between what the debugger knows and what the debug stub needs to know. So the debug stub does not need to know your debug information, your symbols. Only the debugger will know that. So this is an example of a packet from the GDB remote protocol, which is also used in LLDB. It's a text-based packet format, and these things mean something like this. So the $sign says this is the start of a packet. Then you have a packet type, which could be anything from set a breakpoint to query my system, read some memory, write some memory. And then you have a bunch of arguments and a checksum to make sure that nothing got broken while you were sending it down the wire. So for this case, Z0 is a breakpoint packet. I want to set a breakpoint at this address, 400570. And then the one is architecture specific. Usually means how many bytes are in the instruction which you would use to set the breakpoint, like OXCC. And then our checksum is just there to ensure everything went okay. So that's most of what I wanted to cover. How am I from time? Okay, cool. I can cover a little bit more then. Heterogeneous debugging. So this is what I work on, well, not right now, but have worked on a lot in the past. So debugging across CPU and GPU is hard. It's even harder if you don't own the GPU system and you want something which can be used in a generic fashion. So you need to build support in at so many levels of your debugger. Your remote protocol needs to understand whether you're communicating with your GPU or your CPU. Your DWAR threading model needs to understand the difference between CPU threads and GPU lanes or wavefronts, warps, whatever. The debug stub needs to have all this information, and it needs to be able to debug both your CPU and your GPU. And then the user interface, how would you express to someone that I have a GPU with 1,000 threads, and I have some of them which are executing in lockstep and they can't diverge, and I have some which are executing here, and then what if there is a divergence in your GPU? Well, you need to do things like predication, running all of your code for all branches and then masking out results you don't need. How do you communicate that to the user and tell them, oh, here's what's going on your CPU? It's a really hard problem. It's okay if you kind of own the entire platform and you can say, well, I'm just going to define it like this and, hey, oh, I own it, whatever. It's a little bit more difficult if you need to say, okay, I want some kind of understanding of how your threading model works in your GPU. What's your SIMD width? How many threads will I be spinning off? Things like that. I think that the best place to put all this is in the operating system, because then you don't have to deal, the debugger does not have to deal with, I have a thread ID, and I have another thread ID, and one of these could be from the CPU, one of these could be the GPU, and I need to keep track of all of them and understand where they came from. If I have an address, I want to set a breakpoint on that address. How do I know if that's mapped to the CPU or GPU? Well, I need to understand all of the different loaders which the system's using and everything like that. If everything's built into the operating system, then you can just do for the GPU like you do for the CPU in a lot of cases. So you can read the maps file in the procfs for working out where code has been loaded into your address space. And you can let the operating system handle all your thread IDs for you without having to present some consistent model to the user. So I think this is the way which they should be going. There are groups like HSA who are trying to move towards getting some of this into the operating system. And if you're familiar with things like the heterogeneous memory manager, which is starting to get into Linux, then that's kind of doing some similar stuff. And very quickly, a bit about reversible debugging as well. So the super naive mode is just you emulate everything. Right? If you emulate everything, then you know everything that happened. You can just record it and you can play it back. It's easy. But it's also really, really slow. So what you can do is, the fact about programs are most of it's deterministic. Like if you add 1 to 3, you don't expect to get 4 on Monday and 5 on Sunday. You expect pretty much everything to be deterministic. So you can mostly kind of take snapshots or intervals of your program and then just replay the state of the instructions. The problem then becomes you need to capture the non-determinism. So if you're doing I/O or reading atomics, volatiles, if you're doing syscalls, then you need to know how these have changed your system. So what you can do is you can kind of dynamically instrument the code and just kind of translate basic blocks into instrumented code, which will record everything and play it back properly with all of the non-determinism. So I believe that's the kind of approach which Undo and RR take. Undo are outside, so you can ask them. They'll know more than I do. But that is all I wanted to cover today. These are all of the photographers for the cool bugs, which I found online. And here's a bunch of, if you scan that QR code, I've got some resources for learning more about debuggers and object file formats, Dwarf. In particular, I wrote a 10-part blog post series on how to write a Linux debugger from scratch, going through pretty much everything I talked about here, how you would implement it, giving examples, and you'd have a real working debugger at the end of it. So have a go and let me know, and thanks very much. Are there any questions? Yes.
Thank you. Nice talk, by the way. I found out when I was debugging that data breakpoints were much slower than code breakpoints. Is it because of the hardware registers and the way it works?
I would have expected the hardware breakpoints to be faster than the software breakpoints. So I'm not sure why you would be seeing that, but maybe I can have a look and...
well, it's Visual Studio, so I don't know.
Yeah, I don't really know what Visual Studio does, so maybe it does something weird.
Yeah, possibly. That wouldn't be the first time.
Other questions?
Hey.
Hi.
So you mentioned that for the software breakpoints, when we replace the original opcode by this CC opcode, the interrupt, we save the original opcode somewhere. But I think you did not mention who puts it back later.
Good question. So the question was, the microphone's on. So when you save out your the first byte of your instruction, you don't want to forget it because otherwise you won't have executed the instruction which was actually in your program. So when you continue from the breakpoint, there are a few different methods, but the simplest one is just set the byte back to what it was. So get rid of the OXCC, put back the original byte, single step over that instruction, and then put the breakpoint back. Because unless the user's asked for a single hit breakpoint, you want it to be hit if it like loops round or something. So you need to like step over once and then put it back. GDB, I think, implements a bit more of a modern version called displaced stepping, where instead of just doing a single step over the instruction, what it does is allocates some memory in your address space, puts the old instruction there, fixes up it adds an instruction to jump to to after the breakpoint, and then just continues from there. So it doesn't have to do a single step and then continue. It can just set the program counter and continue. So that actually works a lot better if you're doing non-stop mode, where some of your threads will be running while some are stopped, because you don't want to be necessarily modifying your program if some other thread's going to be hitting that code. But it is a little bit more difficult because if the instruction which you're set a breakpoint on is doing some PC relative addressing, then you need to fix that up as well. So it's a little bit more complicated, but more powerful. Thanks.
Thanks.
Any other questions?
So not a question, but I did spot the bug, one you didn't ask for.
Oh yeah.
Yeah, so in the first assembly example, is it intentional that you move from RSP to RSP?
No, that is a bug, and I left it in there because I thought it was kind of funny. So yeah, I'm glad that some people actually read the assembly which I put up. It's great. Any other questions? No, okay. Thank you very much, everyone.